Alright, welcome to the last lesson of Unit 4. Here we are going to find the inverse of a radical function and identify the domain and range of the function. You've probably seen inverse functions before, and so hopefully this example that you're going to do is going to help you confirm in your mind what an inverse function is. So you don't need to copy down all of the words here, just the relevant information. So you know the formula t equals pi over 4 times the square root of 2l gives the period of a pendulum, the time it takes for a pendulum to swing back and forth, t in t seconds, expressed as a function of the length of the pendulum, l, in feet. Here's what you want to do first. You want to find the lengths of pendulums that produce periods of 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds, and 8 seconds. Now, before you go ahead and do this, think about what you're going to have to do. Come up with a plan and see if you can make your method, your plan, as efficient as possible so that you have to do as little work as possible. It is possible to do this in a quite efficient way. All right, once you've done that, go ahead and press play, and we'll discuss what to do from there. Okay, the daunting part about this question is that you see that you are given a bunch of periods, t values, and that you want to find L, which means that you're going to have to do some solving, right, because you haven't solved for L. And you notice that you're going to have to do this many, many times. In fact, 8 times. And when you think about that, you might say to yourself, well, I'm going to be doing a bunch of stuff over and over and over again that's kind of monotonous, but it's going to be time consuming. Is there a way that I can make my method more efficient? And you could by simply solving for L once and then plugging in all your t values into your new function that gives you L in terms of t. So let's take a look at how that would happen. If I start with t equals pi over 4 times the square root of 2l, and my goal is to end up with an equation for L in terms of t, I'm going to have to multiply by 4 over pi on both sides, giving me this equation. I'm going to then square both sides and divide by 2, or multiply by 1/2. So here I am squaring both sides, right? I have 4 squared, which is 16, t squared, which is t squared, and pi squared, which I'm just going to use pi squared there. And over here I have 2l. I now multiply by 1/2 on both sides. And this will allow me to isolate L. In other words, I will now have an equation for L. So L is equal to, notice on the left side here I have 16 divided by 2, and that is 8. So I'm going to have L equals 8 t squared over pi squared. Now, you could certainly take 8 and divide it by pi squared to get one coefficient out front. You're more than welcome to do that. But regardless, I now have an equation that allows me to input a t value, square it, multiply by 8, and divide by pi squared, and that will give me the corresponding L value, or the length that I want. So now you can go through and you can find the lengths for the pendulums that produce a 1 second period when t is 1, a 2 second period when t is 2, so on and so forth. So go ahead and use this equation to do so. You may use a calculator to approximate, and once you've done so, press play and we'll look at the last part. Okay, so hopefully that was a lot less painful than you might have originally thought. Now, what we want to do is look at the formula for t and the formula for L. How are they related? So what I'm going to do is I'm going to bring this formula down here, and I want you to spend about 2 to 3 minutes looking at the two functions and asking yourself, how are they related? What type of functions are they, and how are they related? Well, let's take a look. So t is what type of a function? It is a radical function because I am taking the square root of the input variable L. L is not a radical function. L is a function of t that is being squared. So this is a square function, or what we call a quadratic function. What's the relationship between a square and a square root? Remember, they're inverses of one another. And so that's why we call these two functions inverse functions of one another. In other words, one gives you t if you plug in a value of L, and the other will give you L if you plug in a value of t. And this is exactly what we mean when we say inverse functions. So whether we're working with t and L, or we're working with x and y, inverse functions mean the same thing. It switches the role of the input and the output variable. So here's the definition of an inverse function. So if you start with a function f that maps a value of x to a corresponding value of y, let me denote that here. Take a value of x, and the function f will map it to a corresponding value of y. Then the inverse of f, or f raised to the negative 1 as it's written, maps a value of y to a corresponding value of x. So what we can say is the inverse will take some value of y and map it to a corresponding value of x. Now I want you to go back to your discovery problem and relate this to the discovery problem. What we started with was a function that gave you t in terms of L. In other words, if you input an L value, your function would take that L value and map it to a corresponding t value. Then we found the inverse, so that we could then input a t value and map it to a corresponding L value. Now it's usually helpful to see this done in an example so that you can then sort of put together how this works. So we're going to start with a function f of x as defined by the square root of x minus 2. And if our goal is to find the inverse, what I want you to first think about is if we have a square root function, the inverse should be what type of function? Well, it should be a squared function, right? Or a quadratic. And so knowing that ahead of time is going to make it very helpful. All right. Now, what I want to do is the same process that I went through in the discovery problem. I want to solve for the variable that is currently the input variable, or the independent variable, right? Because I'm reversing the roles of x and y. So it is helpful to rewrite, using function notation, f of x as y, square root of x minus 2. And my goal now is to solve for x, so that I can have a function that does the opposite of what this original function does. So I'm going to square both sides. That leaves me with y squared equals x minus 2. Then I'm going to add 2 to both sides. And this leaves me with x all by itself. So x is equal to y squared plus 2. And here I can see that I have the inverse of my original function. Now, at this point, what I want to do is rewrite using function notation. And the reason I want to do that is that I always want to have my input variable be listed as x. That'll help us out when we go to graph these functions. So I'm going to rewrite this scenario here using my inverse notation so that I can change the input variable back to x. So notice that what I'm going to do is I'm going to input my variable, square it, and then add 2. I just want to change that input variable so that it's x. So I'm going to have f inverse of x, and that's going to be x squared plus 2. So even though I'm using the same variable here, I know that it's a different relationship, and it's an inverse relationship, and I can see that given the inverse notation that I have here. To prove to you that this works, let's go ahead and find f of 6. F of 6 is the square root of 6 minus 2. 6 minus 2 is 4, and the square root of that is going to be 2. So if my original function, I input some value, 6, and that function gives me an output value of 2. My inverse should do the opposite. In other words, I should be able to input a value of 2, and my inverse function should take me back to 6. So let's see if this works. What is f inverse of 2? Well, it's going to be 2 squared plus 2, and that, of course, is 6. So if you didn't believe me, hopefully you do now, that this is in fact the inverse of the function f. Now, I want you to write down the process that we went through. So notice the first thing that we did before we did any work on our paper, we asked ourselves, what should the inverse function be? What type of a function? If we're dealing with a square root function, the inverse is going to be a square or a quadratic. Then I replaced my function notation with an output variable. So if I have f of x, I replaced it with y so that I could more easily solve for x. I'm switching the roles of the two variables. Once I've solved for x, I then have my inverse function. I just want to rewrite it using inverse function notation. So what I did was I rewrote the input variable as x and used inverse function notation to denote that that was the inverse of my original function. Okay? So I'm going to give you a couple to practice. I'll do the first one so that you can see another example, and then you can finish them out on your own. All right, so here are the problems you want to try. I will show you the first one, but you should try the first one on your own, and then press play, and you take a look at the solution together, and you can finish the rest out on your own. Okay, so first I want to visualize what the inverse function is going to be. Since this is a square root function, I know the inverse is going to be a square function. Once I have that, I'm going to go ahead and replace g of x with an output variable, call it y. So I have the square root of x plus 3, and then I'm going to go through and I'm going to solve for x. This will give me y squared minus 3. So now I have my inverse function, and I'm going to rewrite it using inverse function notation. It's the inverse of g. So g inverse of x now, I'm rewriting my input variable, is x squared minus 3. And you could check to make sure that works. You could input an x value of 1 into g. g of 1 is going to be 2. And if you input 2 to your inverse, e inverse of 2 is going to be 2 squared, which is 4, minus 3, which is 1. So you can see that they have the inverse relationship. All right, continue out with 3 through 5, and we'll take a look at them in class tomorrow.